Okay, welcome everybody. Welcome to the teaching module Monitoring and State Estimation. As you already heard from the motivational video, we're talking about Kalman filtering or state observation in general. And for that, let's start with what is that we need to do in monitoring or state estimation. So when you think about our plant as a system that we have, that has an input vector, which always has some process noise. We call it W in this case, and we have our output that we can measure. So in general, most process values are measurable or observable, but in a lot of cases in real processes, we have a problem that not all values that we need to characterize a state estimation or a state of a system, that we can't really measure them or observe them. To solve this problem that we do have state values that we cannot observe directly, we can use something that is called a state estimation. And for this, we can also, for our plant, have a mathematical system that in general we will call the state estimator or state observer in general. For this, we use our process inputs from this side as an input for the state estimator, but we can also use our output we have from our process or our plant, the system, which we can then use to estimate the current state of our system to, in the end, make conclusions in regards to quality. So for example, if we have a bioprocess, in a lot of cases we cannot directly measure biomass concentration. So we could use a state estimator that uses inputs like input substrate concentration and maybe measured output values like temperature or oxygen concentration to, in the end, measure or calculate the correct state of our biomass concentration. So this is our system. So we have our state observer or state estimator, which uses process input U and process output, which is measured Y. So as an example, we can look at a very simple case where we have a linear system or a linear dynamic system. And we also say that all noise in the system, be it process noise or here sensor noise, is Gaussian. So we have our system, our linear system, which can be described as So for this, we have our x from k, which is our state vector, which describes the system. We have our matrix that describes the state transition in the system. We have our system matrix that describes our input vector. So for that, we have our state vector, which is unknown. We have our state transition, which can be known and unknown. We have this one that is known. And then we further describe our system as right y from k with h from k, which describes the observation matrix. And which is also described by our noise. Which is, as we in the example before described, Gaussian for this example. Okay, so all of our matrices are described in the end by our covariance matrix, which is Q from K. And R from K. So when we have our system, our linear dynamic system, which we can describe with this, we can use then our state estimator to perform a simple observation for a next step to estimate the state of the system. We can use different kinds of state estimators. For this tutorial, we will talk about different kinds of Kalman filters. We have a simple Kalman filter, which we will start in the next video, and then we will have more complex ones to describe nonlinear system like extended Kalman filters and unscanted Kalman filters. So in the end, what we try to do with our estimator is describe is that in our system, we have our states and our measurements, and we can use those for each individual time frame or time point to calculate our current corrected state. For example, these different ones. So this also helps us to correct noise in the system. For example, our sensor noise, which is V, and our process noise, W. So in any case, we would have a very simple process of calculating the state estimation with a simple general observer, where we make it very simple, leave out the W for process noise and just say in the first step, we predict what the state is. Our prediction for our state and the estimated state with our inputs U for the estimated state. After we've done our prediction, we want to calculate our correction that we can use to adjust our state in regards to process noise and sensor noise. So, second step after a first prediction is to compute the correction. So, what the difference between the actual state and the estimated state actually is. So once we have computed our correction, we can then, in the last step, update our prediction that it actually is closer to the actual state than the first estimated state. So we have our first prediction plus our updated difference in whichever each direction is necessary. So, but this only works for very general assumptions. So if we want to use a state estimator for a more complex system, be it something that is not linear or something that does not have just Gaussian noise, then a simple state observer with these 3 steps is not enough to give a good estimation for our system. And so in the next couple of videos, we will be talking about first the better option, a general Kalman filter, which we can use for linear systems or very not complex systems. And then in the next video, we will be talking about the extended Kalman filter, which we can use for nonlinear systems, and unscanted Kalman filter for very complex systems, and we will make a differentiation when which Kalman filter is the best to use and the easiest to compute.